Thank you, Ellen. Again, my name is Mike Fuller. It's a real pleasure to have so many great faces and so many great subject matter experts in the area of astrochemistry and astrophysics. Just a quick housekeeping note that I always forget myself. If you were in the room, if you could please make a point to just double check your phone, make sure it's on silent, because we don't want to disrupt the speakers that have come from all over the U.S. to give us some great presentations. So to that end, our first speaker today, our keynote speaker, is going to be Dr. Paola Caselli. She is the director of the Center of Astrochemical Studies at the Max-Planck-Institute for Extraterrestrial Physics. She's also a visiting professor in the Department of Astronomy at the University of Virginia and the Jubilee Professor at Chalmers University of Technology, Gothenburg, Sweden. Paola's work includes observations, theory, and laboratory experiments related to astrochemistry and star and planet formation. She received her PhD in astrophysics at the University of Bologna, which included some time working with one of our other co-organizers for the workshop, Dr. Eric Herbst, as well as some time with Dr. Phil Myers on molecular cloud observations at Harvard-Smithsonian Center for Astrophysics. So to that end, I'd like everyone to please welcome Dr. Paola Caselli.
Okay, sorry, give me 1 minute. I need to, maybe if I can get some help, Jessica, can I ask you please? My problem is that I cannot see the
You're totally fine.
The Zoom anymore.
You're totally fine.
I hope.
Your clicker is so strange.
Aha.
Oh, so how do I click?
I don't understand what's going on now. Of course, before it was working perfectly.
That's the way things work. I don't know how to...
I can turn off this. Let me see if I can.
Oh, you have so many things open.
Yeah, but you see, at Zoom, it doesn't work. I'm not sure why.
Here, can we go back to your email?
Mm-hmm.
Where's your email?
Okay, I will. I just click this away. Close. So here's the email.
So click the link again.
So maybe it was, for some reason, was allowed.
Oh,
okay.
Are you German?
Well, I work in Germany.
Oh.
Yeah. So maybe I should switch off the email first, because otherwise I keep having these messages.
It won't pop up if
you'll see. Share. Okay. Perfect.
So which one is it?
All right. So this is the. Let me see.
Is it that one?
The Washington. Yes.
Okay. Share screen.
Share screen. And then I just play. Okay. I think it should work.
Okay. And then you know what I'm going to do for you? I'm going to get rid of this.
That's perfect.
And okay. And at the end, at the end, you're just going to press stop.
Okay.
But for now, you advance the way you normally would.
All right. Thank you. Thank you. Okay, we made it. So thank you very much for inviting me here. It's an honor, great pleasure to be here. So what I will do today, I will talk about my work and what actually motivates my work. So here in this first slide, you see some pictures that basically take us from the very beginning of our origins, which are these molecular clouds that are in the galaxy where we are. Within these clouds, stars forms, around stars, planets form. And this is, for example, a very young protoplanetary disk, something similar to what our solar system had 4.5 billion years ago. And these rings are actually locations of new planets. And, you know, all this material that make planets is initially in these tenuous clouds. So there are all the ingredients from organic molecules, like at the origin of prebiotic molecules and life, to solids that form planets. And then, of course, you know the rest of the story. You know comets, you know planets, you know Earth, you know life. So let's actually move forward if this works. Yes, the problem is that it's not advancing. I knew that. I'm so sorry.
So do you normally just...
Yeah. Maybe, how did you do that? Okay, so now it works. Magic. Jessica. Thank you, Jessica. So hopefully from now on I will not need your help anymore. So these are the interstellar molecules. You don't need to read them. In fact, on purpose, I put them quite small. The only thing I'd like you to notice is the slight different change in color. So we go from pink, these are inorganic molecules, and this kind of grayish color is organic molecules. So this very large majority of molecules that we see in space are organic in nature. Many of them are actually quite interesting because they are precursors of prebiotic molecules that I'm sure you have heard about. For example, this is amino acetonitrile that was discovered in a star-forming region in our galaxy. You see 2 nitrogen, 2 carbon, and 4 hydrogen atoms. This is just one step away from glycine that we have not detected yet in space, but we know that is present in large amounts in comets and also in meteorites. And this is actually a new table that was done by Brett McGuire. He's an NRAO at the moment. And these are all the molecules with 8 atoms or more that has been detected in space. So you can note actually that there are quite large assembling of carbon like these fullerenes. Another piece of the story that actually motivates my work is the fact that we see complex organic molecules and actually prebiotic material in pristine material in our solar system. So these are the building blocks of the planets. And some of this material has rained down on our Earth after it was formed. We had 1 billion years of heavy bombardments, and some of these pieces that rained down were actually rich in organics and water, and may have brought in some of these important building blocks. And in particular, we have amino acids. You know that in life we only use, not just us, but all the living beings on Earth use 20 amino acids. In some of these meteorites, we see more than 200. So we have all kinds of different forms of amino acids. We have fatty acids that are actually important for making membranes of cells, nucleobases, like, for example, guanine, adenine, and uracil, that makes up the famous RNA and DNA polymers. And these are just some examples. So it's like having these Lego boxes coming down, full of stuff that needs to be assembled and then to form living beings. And in fact, recently, in 2018, this year, there was a paper in the PNAS, very nice paper. In fact, it won the prize as the the best paper of the year of this journal, where some pieces of the puzzle were put together. So you have this rain of meteorites that brings in organics, prebiotic molecules. We have our little warm ponds in the early Earth that presumably they were there. We know the liquid water was on the surface of our planet almost soon after the formation of the Earth. And then with some cycles, like a dry and wet cycle, some photodissociation from UV photons, hydrolysis. Actually, these people here, this is a theoretical paper, point out the fact that RNA may have actually formed more than 4.17 billion years ago. And the Earth was formed 4.6 billion years ago. So we presume that life also started very early. We still don't know how life originated, but we know that basically all the ingredients are there, and we just need to put things together. And this is why we are also working with the biophysicists and people who actually work on more advanced, stages of evolution. Of biotic material, prebiotic material. So this is the outlook of my talk. Just to give you a flavor of what we're doing, also in collaboration with the people who are sitting here, of course, Professor Herbst, that was one of my first advisors, and other people. So I will take you through these steps, going from these dark clouds and down to protoplanetary disks. At that point, I will stop because my colleagues will actually move forward on that part, and then from that on, we have planets, and we probably have life. So let me start with our Milky Way. This is an optical picture of our galaxy, and you can see, maybe not so well, but you see that there is a bright stripe, and these are stars that are not resolved individually because they are so far away. That's why our galaxy has been called Milky Way. Looks like like just a stripe of white, bright light. But then, if you look carefully, there are quite a lot of these dark patches, and these are clouds. So these are the dark clouds where the new generations of stars and planets are going to be forming. And these clouds are dark because are filled with gas, of course, but also dust particles. And these dust particles are tiny, sub-micrometer size, and they can absorb the light from the stars in the background, and then you don't see the light, you see the darkness. So this means that the optical telescopes are not good for us because we can't see anything. We need to look at actually radio wavelengths, and in particular, we need to look at molecules. And in fact, where it is dark, we see very bright emission of molecules, and this is the most abundant molecule after molecular hydrogen that is in our universe, and which is carbon monoxide. Now, carbon monoxide is so abundant that the lines are really optically thick, so we cannot go through very much. That's why we need other molecules to actually see through and understand the physics and the dynamics of these clouds. If you look, for example, with Herschel, this is a 500 micrometer continuum, you see that in some pieces of these clouds, there are very bright spots. And this is where we want to look if we wanted to understand how stars and actually eventually planets are forming. These are the so-called dark clouds. Of course, they are bright at 500 micrometer because this is close to the peak of the emission of material that is about at 10 Kelvin. This is what is the temperature of this region here. As I said, they contain dust grains, interstellar dust grains, that the core, the bulk of these dust grains is morphosilicates and carbonaceous materials. The sizes goes from 10 angstrom to about 1 micrometer in size. So, zoom in again. Here we are now in the AU, just in case this is astronomical terminology. So 1 astronomical unit is about 8 light minutes, is the Sun-Earth distance. So if we go to the 10,000 astronomical unit, we are now getting into the so-called pre-stellar cores. So these are the hearts of the clouds where actually stars are forming. And in the dust millimeter, now we go to millimeter dust continuum emission. It's getting really cold. I'll show you how cold it gets. And here we see a central, very bright peak. This is the center of action where everything will form later. So everything means stars and planets. And there are various zones that we have recognized that are differentiated by the type of molecules that we see. This is where astrochemistry becomes important because we need to understand some basic astrochemistry to actually understand which molecule to observe to study the specific part of the cloud that we want to study. How cold it gets. Again, molecules, and in particular in this case ammonia, which is the best thermometer that we know. And also it's great because it remains in the gas phase also at high densities, so it allows us to actually measure temperature in the center of this dense region. And by dense, I mean more than 1 million H2 molecules per cubic centimeter. So it's very low density for our standards, but it's dense for these clouds that typically have 1,000 H2 molecules per cubic centimeter. So here, using the VLA, this was work done more than 10 years ago, we saw that going toward the center of the cloud, the rotational temperature that is proportional to the kinetic temperature of the gas goes down to less than 6 Kelvin. So you have to imagine these dust grains and the gas so low temperature that in fact some of the molecules that hit the dust grains will just be stuck on it and form thick icy mantles. This is the beginning of the coagulation of these dust grains. These icy mantles will be mostly made out of water and CO and other molecules, also complex molecules, but we don't have the sensitivity yet to see this. That's why we want JWST to go up and look at that for us. One way that we know that there is a heavy freeze out is looking at CO emission. And we see that where we see the dust peak, we actually see a nice hole in the CO emission. This means that CO molecules disappear. They disappear, and in fact, again, we think that they form this thick, icy layer. We also know that there is CO freeze out and other molecular freeze out, because when we look, for example, at the stars that are behind the clouds or inside clouds, so in this case, young stars, and we see through and we try to look at their spectra, we see in their spectra absorption features, and these absorption features correspond to, of course, silicates, because I told you the bulk is silicates, but we also see water ice, we see methanol ice, we see carbon dioxide ice. So there is no question that there is ice on top of these dust grains, and these are the precursors of planets. So let me go through very quickly to some basic astrochemistry. And I think I need to do this just to let you understand, for some of you who are not familiar with chemistry in space, how things work there and what are our main ingredients and why we get so excited when we talk about dust. So the formation of H2 is step number one. And we know since the early 60s, and this was work done by Gold and Salpeter, theoretically, to understand the observations of H2 molecules in diffuse clouds in our galaxy, how H2 molecules can survive with this harsh environment. We have UV photons dissociating H2 all the time. It has to form at a high rate. And this high rate, nobody was understanding how could it be unless you actually take into account the fact that you have dust grains and hydrogen atoms can land on top of dust grains, sweep around very quickly, meet possibly other hydrogen atoms, and when they do that, they form H2 molecules. And when you form an H2, or anyway, a molecule on the surface of the grains, the formation energy of the molecule allow at least a fraction of these molecules to go back in the gas phase. And this was basically the solution of the problem. The rate that was found that actually can be is, of course, proportional to the number density of a hydrogen atom, their thermal velocity, the sticking coefficient, etc., is actually in the right bulk order to understand the H2 in space. Even in regions where you have enhanced UV field, for example, close to star-forming regions, you have to enhance a bit the formation rate of H2, and this is done thanks to the fact that there are PHs, these polycyclic aromatic hydrocarbons, that are quite a lot of these small dust grains or large molecules, as you wish, that provide a lot of surface area for the production of H2. Step number two. After you form H2 on the dust, you have another ingredient that is extremely important, and these are the cosmic rays. These are relativistic particles that basically are injected in the interstellar medium by supernovae. So when the stars die, the massive ones, they explode and inject relativistic particles that provide a sort of ionization and dissociation. And this, for example, for H2 molecules, 97% of the time, a cosmic rays will ionize it, producing H2+. Once you form H2+, and in a molecular cloud, H2+ will react almost immediately with another H2 molecule, forming the most important molecular ion in astrochemistry, which is H3+. H3+ is an H2 molecule with a loosely bound proton. And this loosely bound proton is what we need because once it finds, for example, atoms in space, like oxygen or carbon, it gives it to it. So it forms for the oxygen OH+, for the carbon CH+. And then there are this series of abstraction reactions that get more hydrogen until they can. For example, here for the oxygen, we arrive H3O+, and then Nothing else can be done, so you cannot add another hydrogen, so electrons can dissociate, and look, you form water. In the other case, you start to form hydrocarbons. So this is the beginning. We also need dust grains, first of all, to form H2, but also we will see that many of the molecules that we see in space is very hard to understand their formation, especially the highly hydrogenated ones, if we do not take into account the dust grains that act as catalysts. In fact, here, this is a very simplistic view. This slide I took from Eric Herbst for some old talk that he gave, but it's very, at least it shows the main paths. So we have assumed that this is the surface, very simplified surface of a dust grain. We have, of course, the accretion of an element or a molecule. This element, especially if it is light, can desorb, like hydrogen, or it can thermal hope, or in case of hydrogen and deuterium, so the lightest elements, it can quantum tunnel through. So it doesn't matter if it is very cold at all, and can actually go in other sites, meet other partners, make new molecules, and some of these can actually form. This is called the Langmuir-Hinchelwood chemistry on surface, but there is also the Ely-Rideal chemistry that is just an atom, for example, acritic on top of an occupied side, and then you form a molecule. This has been used a lot in chemical models. What do you do? Well, I told you already that you make a molecular hydrogen, but if instead of another hydrogen you encounter, for example, an oxygen, well, you form water quite readily, and this has been proved in the laboratory as well. If you have a carbon atom, you form methane very soon because hydrogen sweeps around very quickly. And the time scales are here, fraction of a second sweeps around the surface of a grain. With nitrogen, you form ammonia. And if you have CO, especially in this region where CO is frozen out, so in the very center of this prestellar core just before forming a star, well, you go through this hydrogenation chain and form methanol. And we see it, in fact, methanol also in ice and, of course, in the gas phase. There is no way to form actually methanol in the gas phase at the abundances that we observe it. So we need dust. Once you have actually the dust surrounded by this icy mantle, you see that you have lots of molecules. These are the ones that we think are there. Some of them actually we see them, as I said, water, methane, methanol, CO2, ammonia, and CO. And OCS as well has been detected. And then there are lots of processes going on that can actually make things complex in this ice, even if the temperature is very low, and including some UV field that is produced by cosmic rays when they go through dark clouds. In the dark clouds, you don't have UV fields, but they can be produced by cosmic rays because they excite H2 molecules that then fluoresce back and produce this tenuous UV field. And you have the cosmic rays. The cosmic rays just don't care. The densities are so low in these clouds for them that they just go through, do their damage. They hit ice and they break bones. They inject energy, and you can make a lot of interesting chemistry. And this is all something quite new that, in fact, Eric Herbst and his former student, Chris Schindler-Decker, who is now with me with the Humboldt Fellowship in Germany, he is working exactly on this project, and we are putting together pieces of his thesis, irradiation of ices with protons, and also taking into account heavier nuclei, like iron nuclei, that are supposed to actually inject a lot of energy in these ices. So work in progress. So I have been discussing a little bit about, just mentioned deuterium, but I would like to say a little bit more about this because this really touches us quite closely because our ocean is enriched in deuterium. And there is not a good reason, if we don't link to space, to understand this. And in fact, here there is the D/H ratio. This is the Earth ocean. You see that there is about 1.5 times 10 to the minus 4. The ratio. If we look at the cosmic deuterium abundance, so D/H in the universe, we talk about an order of magnitude less. So how do we make this extra deuteration? Now, here we compare the Earth ocean with comets. They have enough DOVH, actually even too much, a little bit higher. There is actually one comet just spot on at exactly the same DOVH. Carbonaceous meteorite, the CI especially, they have exactly the same DOVH. We go back to what I said at the beginning about the heavy bombardment. These pieces were actually falling down on Earth as soon as it formed. So it must have come, or could have come from these pieces that actually are relic of the early solar system. So how this is possible? We understand this in space because in cold regions, when H3+, that I already introduced you, reacts with the heavy H2 molecule, so HD, it forms H2D+, and this is an exothermic reaction. So this is the exothermicity, 230 Kelvin. So in cold regions, the reaction that goes backward is basically not proceeding. So you get a higher and higher H2D+ or H3+ ratio. Once you enhance this ratio, you can see that the deuterium to molecules like CO and to other atoms, etc., enhancing the deuteration around. And also, when you freeze out molecules like CO that destroy both H3+ and H2D+, you enhance even more. This was pointed out by Alex Dalgarno and Steve Lapp in '84, and this can be understood just looking at this simple picture here, where there is a destruction mechanism of H3+ and H2D+, that in fact form the CO+. When you freeze out CO, you lower down the H2D+ and H3+, destruction rate. You increase the formation rate of H2D+, because this now has a higher abundance, and the two things together give you this larger ratio. It doesn't stop there. It goes all the way to D3+, this story. And this, in fact, we know because we have observed also D2H+, both ortho and para forms. We are trying to observe D3+. This is not easy. We will try more. For the moment, we have upper limits. But what this is all giving us, it gives us a lot of deuteration for other molecules, but also a lot of deuterium atoms, because once they recombine with electrons, they actually produce deuterium atoms. These deuterium atoms compete with hydrogen atoms to hydrogenate or deuterate the molecules that are on the surface of dust grains. So we expect that once we have such a high freeze-out rates in these cold regions, you enhance a lot the D/H ratio, and you produce a lot of deuterated organic molecules like methanol, because you have CO on the surface, and you have seen that CO goes to methanol or deuterated methanol, and this is exactly what we see. We actually see a lot more of the deuterated organic molecules, for example, in the form also of triply deuterated methanol, compared to the deuteration of water. Is orders of magnitude more than what we need to understand, for example, the deuteration of our oceans. So we think at least that this part of the story we understand by just a ice formation time. And in a sense, I already told you this, but I'll just give a little summary of this part. So again, we have our cloud. This is the center of the cloud, the prestellar core, where the stars and planets will form. This is where CO is freezing out very heavily. In the outer part, we have just a little bit of ice. Most of this is water ice, and here the deuteration ratio is not very high at all because it's still warm, and also you don't have much freeze out. So, you mostly here you have a little bit of like the cosmic abundance, 10 to the minus 5. Once you get toward the center of the, closer to the center of the cloud, you enhance the deuteration, and you start to have a bit more deuterated water here. And you build up a lot of this water, so this is probably the origin of our oceans. As you move in more, you get this CO freeze out, and you have a lot of deuterated methanol. And methanol is a precursor of other complex organic molecules as well. If we look at our meteorites, so again, the carbonaceous chondrites, but also IDPs, so interplanetary dust particles, what we see a very similar story. We see deuteration of water that is very similar to what we see also in space and in our oceans, as I already told you. So of this order here, few times 10 to the minus 4. If we look at the organic material, what we see is enormous enhancements in deuteration. And this is just what I showed you before. This is what we see in space. 15N, 2 slides on this because there's still a lot of work going on and things may change soon, but the things I'm going to tell you are not going to change because these are facts. And this is, again, a plot similar to the deuteration. For some reasons, in this case, we prefer to put the rare isotope in the denominator, maybe just to keep us, attentive and don't lose the concentration. So now we have large numbers here. So 14N over 15N. The Earth, as you see here, is about 270. The ratio between 14N over 15N, this is coming from our nitrogen in the atmosphere. Cosmically, and in our, say, so-called pre-solar nebula, is much higher. So it means that you have a lower amount of 15N. So again, we see some enrichment of the 15N. The interesting thing here is that we see some differentiation. When we look in space, we see that, for example, molecules that contain nitrile and amine-bearing interstellar molecules, there is a significant enhancement in the 15N. You see these values here, this ratio now become low. While the nitrile get high fractionation, the amine and also the N2H+, so ones containing, for example, the ammonia or N2H+, they don't get much enrichment at all. So there is this differentiation between these two different types of compounds. And when we look at the meteorites, we see also something similar. So I will just say a few words here. First of all, in some, the so-called hot spots of meteorites, we see large excesses of 15N, like with the ratio between 14 and 15 up to 65. Also, we see that there is not much correlation between the 15N enrichment and the deuterium enrichment. And this is also what we see in space. And finally, this is actually the latest result that was in last year. The group from Copenhagen, they found that actually there are differences between the functional group. So this is 15N fractionation in CN and NH2 functional groups. We have much larger fractionation in this CN, so nitrile type of molecules, than NH2 and NH. Again, very similar, or say identical, to what we see in space. So there is some kind of heritage that we are still not understanding completely, so all the steps. How can it be that some of the material is actually remaining down to the stage of planet formation with all the irradiation from the young sun, and etc.? Few words about complex organic molecules. This is a beautiful picture put together by Ted Bergin, who is also here. This is from Orion, an active star-forming region. Well, how can you see all these molecules? Again, you have to think that all these thick ices that have been produced during these early phases of star formation, cold phases that have accumulated, once they get close to the protostar, they get heated up, they can be smashed. Not all of them, though, because I just told you that we actually see some evidence of pristine material in our solar system. But a lot of it, and it's actually how much? Enough for us to see. We see actually these molecules coming off very next to the protostar with amazing, beautiful spectra that, in fact, this is where spectroscopy becomes of importance because we have sometimes no clue of what we're looking at. We have zillions of lines, and as I showed you just before, and some of them are still unidentified. This is where we need this very high resolution spectroscopy. However, to know the origins, we need to go back to these early phases. And in fact, again, we go back to the prestellar cores, because already there we see several of these organic material. First of all, this is the same prestellar core, although it looks kind of different beasts depending on where you look. It's just because different families of molecules like different parts of the core. And this is due to the fact that the core is not a uniform sphere, nicely isolated in the universe. It sits inside the complex cloud, and this complex cloud has different sites of where the interstellar radiation field can hit mostly one side instead of the other. So this is exactly what we see. Some of the molecules are sensitive to this external environment, and we need to understand this. This is also where molecules are so important as tools for us to understand the physics of these regions. So you see that HCN and other N-bearing molecules, notice there is no oxygen there, like to be close to the center. They don't like to be on top of the surface of dust grains for some reasons that we're still trying to understand. And other molecules, like, for example, oxygen-bearing molecules, avoid the center. The center is this little triangle here. And they like to be in different regions, either north or south, depending if you like UV photons or not. If you don't like UV photons, you get away from the UV, which is here. If you like UV photons, so these carbon chains and long, like also cyanopolyions, are actually down here. These are the organics that we see. We see several complex organic molecules that it's really hard to understand how they're forming at these low temperatures, unless, again, we take into account at least partially the surface chemistry that allow some of these elements to be highly hydrogenated. We also see differentiation. Again, organic molecules rich in oxygen don't like to be in the center. They like to be where actually methanol is. Nitrogen-bearing molecules, even the complex organic, have the strongest line toward the dust peak. And we know that how this can work with some simulations that we did with this, led by Anton Vasyunin, who actually was also in Virginia with Eric some years ago. Then he moved to Max Planck. And here we look at the evolution of the abundance of these organic molecules. This is the center of the cloud. This is the outer part, showing that actually the oxygen-bearing molecules really like to be in this side. So we think we understand this part. The nitrogen-bearing molecules is still a puzzle, and this is something to work on, and we are working on. But for this, we can understand this with the fact that this is the region where you have this CO freeze out, the surface of the dust becomes rich in CO, and this actually makes the desorption upon formation of molecules on the surface easier, and they can get off, and this is what we see. It's important also to remember that there are neutral-neutral reactions, because once you desorb some of the molecules or some pieces of these molecules, like, for example, as I said, the methanol is very important. You can have this neutral-neutral reaction with OH, which is also abundant in this outer part of the cloud. And this was supposed to have actually a very low rate coefficient. Nobody was using this reaction before. So how can it be that it go on at with these rates in these cold environments, very rare encounters? But actually, later on in 2013, Shannon and a group in Leeds, University of Leeds, actually found out that at low temperature, these rates go up. You see, if you just extrapolate from the previous data, you cannot find these numbers here. And this was, I think, a real revelation for the chemistry, because it tells us that actually also the neutral-neutral reaction when you have low temperature can proceed. And this is due to the fact that you get these hydrogenated, hydrogen-bonded complexes that where the hydrogen tunneling actually cannot proceed, and you actually go from methanol to methoxy and water. So when we look at we compare our molecules that we see in space with the composition of the comets, so organic molecules that are seeing comets, we see also a pretty good correspondence. Here there is, say, disks. These are models. But if we look at the Orion, Iris, these are star-forming region, and then we have two comets here. So we have a relatively similar, say, composition that again reflects the fact that at least some of this material, at least the material that is within the comets, has resisted the harsh environment after the formation of the solar system. Let me give you just a few words about, so this is in a way, say, to introduce the protoplanetary disk. Protoplanetary disks, we know they're forming because, well, first of all, we are here. Without the protoplanetary disk that formed our planets, we couldn't be here. And also, we know that there, we see many of them in our neighborhood, in our galaxy. So they must form. There is a little bit of a problem in the theory, and this is something that is an active field of research. This is dynamics, but again, astrochemistry is very important here because astrochemistry regulates a crucial parameter in the physics and dynamics, which is the ionization fraction. In regions that are magnetized, like these clouds that I have shown you, I have not shown you actually the beautiful pictures that we have of the magnetic fields threading these clouds, but we know that magnetic fields are there. They are slightly ionized. We have these ions that are produced, in fact, mostly by the cosmic rays, at least in the dark regions. You have, of course, ions that are coupled with the magnetic field lines, and they tend to follow the magnetic field lines. When you have the contraction of the cloud toward the formation of the future stellar system, what happens is that if the ionization is large enough, you drag, and the coupling between these ions and the rest of the neutral through collision is high enough, you're dragging this magnetic field together with the gas toward the center. Dragging the magnetic field lines toward the center actually is a way to get rid of the initial angular momentum because the magnetic field resists a bit the rotation of the cloud. And the problem with this is that if you lose the angular momentum, you cannot flatten your cloud. And you need to flatten it to form the protoplanetary disk. It's like, pizza dough. This is why we rotate very fast to make it flat and thin. And this is what we need. So this is a problem because when we run these dynamical models, at the end, we don't form the disks. This is the so-called the magnetic breaking catastrophe. We like to use these big words, but at the end, you just don't form the disk. So we have to find a way to get rid of this magnetic flux. There are various ways. You can imagine many groups having their own ideas. We have our own ideas, and this is what I will tell you. And this is just to show you what in a very schematic way we think is going on. So we have the formation first of a relatively massive, maybe pseudo-disk, not really the disk that will form the planets. And this is a few, maybe 100 astronomical units. This disk may fragment and actually form some interesting structure and spirals that we are now trying to find with ALMA. And then, of course, you have also rich chemistry here going on. Now, in our idea here is that, again, we wanted to have a good understanding of the dynamics together with the chemistry, because as I told you, if we do not follow the chemistry, it's very hard to actually understand how these clouds can dynamically evolve, because ions are important to link the magnetic field to the rest of the clouds through collision. So we did that. We included in a non-ideal MHD. Non-ideal means that basically you can have some slippage, for example, of neutrals through the magnetic field lines via processes that, again, have very technical terms, so I'm not going to discuss in detail, but it's all magnetohydrodynamics. And so we introduced the chemistry in this dynamics, simple chemistry that allow us to follow the ionization fraction. The dust grains, again, very important, especially the small ones, because when they are charged, and they are charged, they are typically negatively charged, they are coupling very well the magnetic field lines with the rest of the clouds because they have large cross sections, so neutrals actually feel the presence of the magnetic field. So these very small grains between 10 and 100 angstrom, actually, if we kept them in our models, they were going to basically do the same bad job that basically we were not able to form protoplanetary disk. So we tried to just get rid of them. So we did it for the moment artificially. We are going to do the proper coagulation in the next months. But for the moment, we just got rid of them, assuming that some of these small grains are just, for example, frozen, like the other molecules on top of these larger grains. And when you remove them, was actually something that for us was, again, at least for me, was like magic, because we started to see actually the formation of these disks. So here it's a movie that shows that without, and here with very small grains. So if we keep these very small grains, you see again that there is no way that the disk is formed. You see actually a lot of material ejected. This is the outflow, the wind from the young star. But without the very small grain, we can actually produce, I will show this, again. We can produce also relatively massive disks. And, you can play with these parameters as long as you want, as much as you want. So just changing a little bit, for example, the ionization rate or the structure of the cloud, the initial condition, you can make all kinds of shapes in these disks. That actually, it's interesting that ALMA, what is showing us now, is that every disk has its own personality, its own shape and rings, number of rings, etc. So we think that at least the initial conditions of these protoplanetary disks are very important and can actually explain to us the whole variety of what we see now with ALMA. So the other interesting thing about freezing out these very small grains, that most of them are the pHs, is that for us, it's interesting also to link to the solar system. And this is something we are going to look also in the laboratory. So when you input or say freeze on top of ice, water ice, and also ice that contains CO molecules, etc., some of this aromatic material, and you can process this. Maybe, and this is again maybe because we don't know yet, I mean, it could be nice to see if at the end of the irradiation and the processing, we could recognize some of the so-called IOM, so the insoluble organic matter that is seen in our meteorites. Because again, this could give us some clues that there is some heritage from these early phases. On the other side here, you see the soluble organic matter that is rich in amino acids. This is what I showed you before. Good, so the protoplanetary disks, as I said, I'm not going to say much, just again to link to what I have said on the chemistry so far. Protoplanetary disks, once they are settled down, so there is not much more accretion from the envelope because the envelope is gone. This is the parent cloud that is basically dispersed after a while, also thanks to the outflows and winds from the young stars. You see that there are regions that goes from very hot in the surface because it's irradiated, and also very cold in the middle where you have a lot of freeze out. So these layers here resemble quite a lot what I show you in the case of prestellar cores. Of course, here the densities are much higher, and the coagulation of the dust is actually much stronger. Here is actually a Hubble picture of a protoplanetary disk that you probably don't see very well, but it's very cute because it shows, of course, this thick pancake that seen at John. This is where the planets, future planets form. And then here there is a little bit tenuous red light that is the scattered light from the young star. So it's really look like, the dawn of a future stellar system. I found that picture amazing. And then, of course, we go to another amazing picture, which is the ALMA picture, millimeter continuum, that shows now a disk not anymore at John, but a little bit tilted. So showing us these beautiful rings that most likely contains young planets. What we see there, well, we also see deuteration. We see high level of deuteration similar to what we see in prestellar core, like, for example, DCO plus over HCO plus of 30%. Remember, the cosmic abundance is 10 to the minus 5. So we see processes that are similar to what we saw in cold regions. So it means that also here must be cold. And in fact, this size here, this is the DCO plus. You see, you don't see HCO plus in these regions, outer region here, the deuteration takes over. In the center, you don't see DCO plus because it's too warm for deuteration to proceed. So it looks like it all makes sense, but we still have a lot of questions to answer. This is the work that Karin Ober at Harvard has done, also with other collaborators. And here she showed this. It's very tough here to detect complex organics, but she did at least the HC3N and the CH3CN and found that actually the ratio of their abundances are very similar to what we see in comets. So let me just summarize all these things that I said, just the main points, and then I show you one more slide to show you my group, just a little flash of what we're doing very quickly. So as I said, we started with this prestellar course inside these interstellar clouds. They are relatively dense compared to the ambient densities. So H2 molecules per cubic centimeter, larger 10 to the 6. Central temperature of 6-7 Kelvin. This is a great laboratory for chemistry at extremely low temperature. There is a lot of molecular freeze out. More than 90% of the CO molecules that are in the gas phase are gone from our measurements. The deuterium fractions is very large. And also we saw that these are the first steps where prebiotic chemistry starts, because we see already these organic molecules. We have large deuterium fractions actually all the way from prestellar core to us in our oceans, in carbonaceous chondrites. And we also see difference between deuteration in organics all the way from prestellar core to us, and which is much larger than the deuteration measured in water. Again, this gives us some hints about possibly storage of prestellar ice. Similarly, in interstellar medium and meteorites, there is, so these two things are quite different, but just to show that, again, we see similar things, so different 15N enhancement in these two different type of molecules, CN bearing and NH bearing molecules. No correlation between a 15N and deuterium fractioning, again, in ISM, interstellar medium, and meteorites. The organic molecules, the complex organic molecules, say their abundances are similar in comets and also in star-forming regions. This is what, in fact, Karin Ober concluded her Nature paper with. Solar system chemistry is not unique, and it looks like it is similar at different times of evolution, which, of course, could help us to link the various pieces of the puzzle together. Also, this is a more recent work that we did about this depletion of very small grains that enable disk formation. And actually, it also tells us that we can have a rich chemistry in these ices, including these aromatics possibly. And also it tells us the importance of microphysics, which is, of course, linked to the astrochemistry. And we really need this to be understood if we want to quantitatively link these things together and make a story, a full story of our origins. So just to finish up, this is my group. The group is in Garching, next to Munich, at the Max-Planck-Institute for Extraterrestrial Physics. And it has 3 subgroups, all very much linked together in a sense that it's mandatory that everybody talks to everybody else, because this is how we learn. And we have observations, so try to use as much as possible, of course, ALMA, but also our IRAM telescopes like NOEMA, interferometer, and the 30-meter telescope. We have a laboratory. We have a laboratory to study with high precision, measure with high precision frequencies of molecules of interest for astrophysics, radicals, ions. We have also collaboration with Mike McCartney at Harvard, who is also going to talk, and also with Susanna Whitaker-Weaver in Atlanta. And then we have, of course, the theory that links the two things together. We need, of course, the dynamics, and we are trying to implement the chemistry within the dynamics, not post-processing. It's different. We really need to have the chemistry within the non-ideal MHD models. Then a chemical model, of course, and radiative transfer. And also, we have collaborations and trying to do a little bit also ourselves with the help of chirp pulse spectroscopy, collisional rates. So it's a big effort. And of course, we can't do everything, and we need a lot of friends around the world. And this is probably why also I'm here. And we really need to focus on various experts, and in particular, say, the laboratory part. And this, of course, implies effort from say, government and effort from everybody, because I think we are, getting there, and we don't want to say, leave things just before we actually understand it all. So thank you very much for listening.
Can I use this mic here? Hi, can you comment on the deuterium fractionation in polyaromatic hydrocarbons, and how does it compare against other complex organic molecules?
Right. So in the polyaromatic hydrocarbons, there have been some observations. So it's not something that is full understood. So there are observations that allows us at least to tell that there are the so-called PADs, so polycyclic aromatic deuterated molecules. But unfortunately, I don't think we have enough, understanding of the whole process, because the problem with the pH and PADs is that it's not easy to detect them in these cold regions. So you can see them in the close to high mass star forming regions or in the outer part of the clouds. But there, in fact, as I said, is where you expect to not see much deuteration. So although there is a deuteration, I expect that it could be that later on in the stage of this, for example, when they freeze out on the ice, etc., they could increase the deuteration, but we are still not there yet to understand. And maybe, I'm saying maybe, because actually I didn't even think of making predictions for this, but it could be a good idea, is to look for possible features maybe with the JWST in ice. So that could be for the future. I didn't put the number. Yeah, that's a very good question. And of course, there are lots of debates still going on. When I talk, for example, with my colleagues biophysicists, they say, I don't need you. I don't need astronomers, because I can actually make, all the molecules I want. But then if you look into the details of what they do, they actually have to prepare their solutions with the larger concentrations of molecules, that then I come in and say, okay, where can you find a spot on Earth where you have, for example, all this concentration of HCN? And then we start to talk, with more relaxed, and we start to discuss. Because in fact, that's, I say it's a good question. I cannot give an answer right now. This is actually one of the motivations why I'm actually doing this. And as I showed at the very beginning, when I showed this figure from the PNAS article, if you consider the delivery from space during this heavy bombardment of material that some of it contains both water and organics, you basically have almost all the ingredients that you need. And it's in concentrated forms. This is the interesting part that also for me, we need to underline very strongly. When you have a meteorite that, for example, fragment in space, so it doesn't just splash on the Earth, which may, destroy some of the molecules, although some experiments have shown that actually, yes, you destroy molecules, but form others that are even more complex. Anyway, so you get material that is concentrated, and it could be concentrated in these ponds. So you have large numbers of organics that then you can just need to build up and polymerize and form this larger structure. If you start from scratch, you first need to find these highly concentrated regions, and this is, I think, it's a big problem that my biophysics colleague have, because even if you go to the hydrothermal vents, well, you have an ocean that is actually sweeping things away, and you still have the problem of concentration. So, as you see, I'm not giving you an answer because we don't have an answer, but I'm sure that, in the next years, working together, because otherwise everybody goes in their own roads, we will be able to, give at least more quantitative numbers to you. At the moment, I cannot tell you, 90% of water is coming down or not, but as we have seen, the deuteration of our ocean is very similar to is exactly the same as what it's in carbonaceous chondrites. And also we see that the same carbonaceous chondrites are rich in this prebiotic material. The rest we need to work on.